Well, it's 12:01 p.m. on the East Coast. So, welcome everybody. Good afternoon or good morning, as the case may be, to today's installment of What's Shaking, DFI's webinar series for seismic and lateral loading. My name is Jon Sinnreich. I am the committee chair for DFI Seismic and Lateral Loads Committee. And today we will be having a webinar with Dr. Kyle Rollins. During the webinar, all attendees will be muted. If you have any questions or comments for Dr. Rollins, please use the question box. I will address all the questions at the end of the webinar. And so with that, it gives me great pleasure to introduce to you Dr. Kyle Rollins from Brigham Young University. Kyle Rollins received his Bachelor of Science degree from BYU and his Ph.D. in civil engineering from the University of California at Berkeley. After working as a geotechnical consultant, he joined the civil engineering faculty at BYU in 1987, following after his father, who was previously a geotechnical professor there. His research has involved geotechnical earthquake engineering, deep foundation behavior, bridge abutments, collapsible soils, and soil improvement techniques. He's published over 190 technical papers and supervised over 130 graduate students. He was recognized as the Engineering Educator of the Year by the Utah State Engineering Council and received the Governor's Award for Science and Technology in 2017. ASCE has recognized his work with the Huber Research Award, the Wellington Prize, and the Wallace Hayward Baker Award. In 2009, he was the Cross Canada Geotechnical Lecturer for the Canadian Geotechnical Society, and in 2013, he received the George Osterberg Award for Innovation in Foundation Testing from the Deep Foundation Institute. So with that, I'll turn it over to Dr. Rollins and his presentation on lateral load resistance of piles in liquefiable sands from full-scale tests.
Thanks, John. Pleasure to be with you all today and to share some of our experience with behavior of piles in liquefied soils. Do I have control here? All right, so as we get going, I first want to say that it turns out I'm part of a line of geotechnical engineers. My father, Ralph Rollins, was a consulting engineer and also a professor at BYU, and in his career he performed investigations for over 5,000 structures, and I got to take soil mechanics class from my father. I don't know how that would work out if you had a class from your father, but for me it was a delight, very big pleasure. And he taught me about geotechnical engineering. This is my daughter, Rachel Rollins. She was a civil engineering student at BYU. I don't know if it was a pleasure or not, but she was also got to take soil mechanics class from her father. So I've written a paper with my dad as a co-author and a paper with my daughter as a co-author. This is my granddaughter, Ella, and she's showing some early interest in soil behavior at a trip to Florida on the beach there. So we'll see how things work out for that. We want to talk today about foundation behavior in liquefied sand, and we're primarily going to address laterally loaded piles and drilled shafts, but we've also done work recently to look at a drag load that develops on piles and settlement that occurs due to liquefaction of sandy soils. So if we have piles that are in level ground, maybe supporting a bridge structure, for example, we're concerned about what kind of lateral resistance we might develop, can count on for a liquefied soil. If the soil is sloping and the soil in the red liquefies, we might develop a lateral spread moving down slope. And in that case, the horizontal pressure that was produced in the non-liquefied soil and in the liquefied soil could act to move the structure down slope. So in both of these cases, we're concerned about the lateral resistance we might have. Of course, lateral spreading can cause significant damage. These are reinforced concrete piles that were damaged underneath a building in Nagata, Japan, due to lateral spread. This is a bridge structure in Costa Rica that was damaged. It was pushed, the bridge supports were just, abutments were pushed into the river, and it caused the whole bridge to collapse. We investigated this in 1991. And this is some port facilities. These are the piles supporting the wharf, and you might think, oh, those are battered piles or something, but no, the ground had actually moved down slope about half a meter and led to a rotation of 14 degrees. Of course, that caused this support cross beam to buckle on one side and to have a tensile failure on the other side. And my structural colleagues say, well, that's what it's supposed to be doing, absorbing the energy. Well, it certainly did in this Chilean earthquake, which was at the time the 5th largest in the history of the world. Now, these could all be considered maybe geotechnical failures, but I wanted to point out another bridge, the Rio Australia Bridge in Costa Rica, that we investigated during our study. We had as-built plans. This truss bridge, shortly after the earthquake, fell off its supports and would be certainly a structural failure. If you looked at the lateral spread on either side of the abutments, on either side of the bridge, you saw massive lateral spread taking place, maybe a meter or more of lateral displacement. And you wonder how that bridge would survive that. You can see the abutment, there's some rotation of the piles supporting the piers supporting this. Each one of these were supported by groups of maybe 20 to 50 piles. Hey, we went in and measured the displacement in between, or the length of the bridge after the earthquake, and in most of the time that is within the constraints of within the limits you'd expect for as-built bridge. So the lateral spread didn't cause this bridge to be damaged or to have problems. So this is maybe what you'd call a geotechnical success story. So if we're careful about this, we think maybe we can design foundations even in liquefied soils to perform in an effective way. The studies that I'm going to describe are sponsored by these 8 state DOTs, Federal Highways, National Science Foundation, the Pile Driving Contractors Association, and the ADSC. And we're really grateful for all their support over the years to help us do this kind of research. When we're looking at laterally loaded piles, we often investigate the behavior by treating the piles as a beam with a finite element or finite difference model to analyze this. And the resistance of the soil is modeled as a PY spring. This is a nonlinear spring. The P is the horizontal force per length along the pile, and the Y is the horizontal deflection that might take place at any given depth along the pile. We've gotten pretty good at doing this for clays and non-liquefied sand and other materials. But when we started doing this, there's considerable uncertainty about what the PY curve should be for liquefied soil. If we have a bridge structure, for example, that is shaken by an earthquake, and that soil underlying the approach fills liquefies, the bridge might move, the soil behind the bridge might move into the abutments and produce a passive force that could push the bridge deck off its support or cause it to buckle. We've seen both of those. And in this case, we're finding that the lateral spread displacement is often really driven by this passive force on the bridge abutments. So it becomes important to know how to design for this passive force as well. So if we wanted to model the behavior of piles and lateral spreading, we might first try and estimate the displacement of the ground at the ground surface due to lateral spreading. And you could use techniques suggested by Youd and others, and then define the displacement versus depth profile. And then we could couple that to the structural resistance of the bridge and piles with springs. And one spring could represent the passive force on the abutment. And that would allow us to tell how much of that force would be applied to the foundation. And then we could use additional springs to give us the force that's developed on the piles due to this lateral spreading. And if we can play around then and stiffen the structural elements until we can get acceptable displacement, or if we decide we need to do ground improvement techniques. Okay, so this is the approach. Our research philosophy is that one good test is worth 1,000 expert opinions. When you don't know how things work, you need some large-scale tests, at least some, to tell you how the world really works, and then you can tailor your models to the way the world really performs. But we have to have a healthy skepticism, because not all tests are of equal value. Einstein is reported as saying a theory is something no one believes except the person who proposed it. He had some experience with theories, right? And an experiment or test is something that everybody believes except the person who performed it. So we've got some questions sometimes: for the strain gauge working right? Was it compacted properly? And all these things that make us wonder and make us question our own tests until we feel comfortable with them. These are all quotes from the internet, and I found this one as well. It says the trouble with quotes on the internet is that it's difficult to discern whether or not they are genuine. So be careful about things you see on the internet. They may not be valid. So as part of our work, we've also tried to develop passive force deflection curves for soil adjacent, non-liquefied soil adjacent to bridge abutments. So this is a simulation where we have two 600 kip hydraulic jacks, and we have a simulated bridge abutment with concrete wing walls in this case, and compacted sand backfill. And we've used these tests to develop the passive force versus deflection curves that we talked about a minute ago. We've done tests with parallel MSE wing walls. We've done tests with skewed bridge abutments, which experienced a lot of damage in the Chilean earthquake in 2010. And some things that we've learned from this is that ultimate passive force is best approximated using a log spiral method. Our K sub P is something like 12 to 18, not 3 to 4 like you would estimate with the Rankine approach. The passive force is mobilized with a displacement of typically 3 to 5% of the wall height. And the skewed abutments have significantly less passive resistance, as this is one of the reasons they tend to fall off their supports. For example, our studies show that if you have a skew angle of 30 degrees, the passive force is reduced by 50%. So the skew angle needs to be considered as well. So how can we investigate what happens during liquefaction? Well, we could use laboratory scale testing. We could use small scale centrifuge models and scale them up to large prototype models. We could use large laminar shear boxes like they have at University of Buffalo. The difficulty here is we're having to recreate the soil instead of using what's in nature that's created by long-term aging and has a micro structure to it. We could also go to large-scale testing. We may instrument a site that's highly seismic and hope that all our instrumentation works when the earthquake finally occurs, maybe 10 to 20 to 30 years down the road. You'd have to have more patience than me to do that. We can use vibra-sized trucks like Ken Stokey and people at the University of Texas have used successfully. Or we can use controlled blasting, which we have used. You have to recognize none of these methods is perfect, But hopefully learning from all that we of all the tests that we can obtain, we can understand better what's going on. So our approach was to use small explosive charges in the ground detonated sequentially so that we could cause liquefaction to occur in a large volume of soil, maybe 15 to 20, 30 feet deep and 50 feet long. So we did test where we had a 3x3 group that we'll show you here in a minute, reacting against a 3-foot drilled shaft. We had a high-speed hydraulic ram that could load these foundation elements within the liquefied soil. And this work that I'm going to describe here was done in connection with Professor Scott Ashford, who was at the time at the University of California at San Diego, is now the dean at Oregon State University. So our first opportunity to do this was at Treasure Island Naval Air Station. This was hydraulic fill sand, dredged from San Francisco Bay, so it was in a loose state. And we knew it had liquefied in past earthquakes and provided a great test site. We wanted to characterize our site very carefully to see exactly what was in the ground, did everything we could to do to do that. So we have CPT testing, SBT, dilatometer testing, pressure meter testing, shear wave velocity testing, even radar tomography by Rob Cahan at the USGS. And then we did our typical laboratory testing. This is the soil profile at Treasure Island. We have a cone resistance of around 80 tons per square foot in the fill material, the interbedded fine sand, and a blow count between maybe 7 and 15. Relative density is around 50% in this case. So we did 4 different test sites, one where we had pilot liquefaction to see if this strategy would even work. Then we did test with a single pipe pile loaded against the H pile. We loaded a 2x2 pile group against a 2-foot diameter cast in steel shell pile or drilled shaft, and a 3x3 group of 12-inch piles loaded against a 3-foot diameter drilled shaft. So when I first had this idea, we thought of this idea of blast-induced liquefaction. My mind went back to,
well, that ought to do it.
Movie Butch Cassidy and the Sundance Kid. They were worried that they wouldn't have enough explosives to blow up the safe inside this railroad train. They were successful, as you can see, maybe a little too good.
Think you used enough dynamite there, Butch? Well, that
So I
ought to do
think
it.
you used enough dynamite there, Butch, right? I think they did. So before we did the test with the piles in the group, we did some tests at a pilot blast. We had these 16 charges that are shown in red, 1-pound charges. We detonated them 2 at a time. And we had pore pressure transducers inserted in the ground that could survive the 3,000 PSI blast pressure and still record to 0.1 PSI. And I was a little unnerved when they showed up at the site, California Drilling and Blasting, and the guy said, "Hi, my name is Butch." But they knew what they were doing. We used 2-component explosives that was made of cellulose and nitromethane drag racer, ammonium nitrate and cellular nitromethane. It's drag racer fuel, as I understand it. We'd put those down these blast holes, fill it up with gravel stemming, and then set off the charges. This is a video of our first test.
Water started appearing on the ground surface almost immediately
I
after.
don't know if you can hear the narration, but as soon as the charges went off, we could start seeing water coming out of cracks and holes in the ground. This lasted for maybe about 15 minutes.
Approximately 15
And that
minutes
water
following
is
the blast.
carrying the sand
Vertical and horizontal pore pressure
with it,
transducer
creating
arrays
these
were
sand
installed at the
boils.
site prior to blasting. In
We had
all,
pore
10
pressure
pore pressure
transducers that
transducers
were in the ground,
recorded
and they were
excess
all
pore pressure
recording
following the blast.
90% of the vertical
Excess pore
effective
pressure
stress.
ratios between 0.8 and 1 were measured for 5
So
to
we
6
knew that we'd
minutes
liquefied
following
the
the
ground,
blast.
and
After
we
1
would
hour,
watch these
excess
sand
pore pressure
boils
ratios had
develop with
reduced
time.
approximately 10%.
So this shows a plot of excess pore pressure ratio versus time after the blast. And we're getting between 90 and 100% initially, and then this dissipates with time after the blast. And we're causing liquefaction out to about 7 meters, 20 feet from the center of the array. You can see here I am kneeling down at the site, these great big sand boils. Here's one, several over here. So we knew this is a characteristic feature of liquefied soil. We found out from these tests that we could set off small explosive charges, liquefy a large volume. This was 20 feet thick, 36 feet wide, and 50 feet long. We could maintain that for 4 to 6 minutes. The pressure transducers survived the blast, and we wouldn't produce vibrations that would cause damage to adjacent structures on the base. So this shows the results of a single pile test. Here's the steel pipe pile, 12.75 OD steel pipe pile, 3/8 inch wall. And we're loading against this H pile over on this side. You can see these massive sand boils that were produced by the liquefaction process. I'm showing here the load versus deflection curve prior to blasting in the non-liquefied soil. This was actually loaded in this direction, but I'm putting it in the same direction, flipping it so that you can compare it to the load versus deflection curves after the blast. So this is out to 3 inches, 6 inches, and 9 inches of deflection. And then we cycled back and forth at that level. As we would load the pile in this direction, sand would flow back in behind the pile, which would require us to actually pull the pile backwards to get it back to the zero state. If you compare the load in the liquefied soil, the displacement to get to the load that we had prior to liquefaction, it's about 9 times more deflection. So we see a significant decrease in the lateral resistance on the piles due to liquefaction. Okay. Go back here. You might notice that there's in this zone here, there's very little resistance. This is just the resistance of the pile primarily. As the soil starts to shear more, it begins to dilate during shearing, and that leads to a decrease in decrease in pore pressure or negative pore pressure. So going from a liquefied state, as we load it laterally, the water pressure decreases due to this dilation. And as it does so, based on effective stress principles, as the water pressure goes down, the shear stress goes up, and we see an increase in lateral resistance. So that leads to this concave upward shape that is also typical of what you would see from a triaxial consolidated undrained cyclic triaxial shear test. This from Boulanger and others at UC Davis. So this was also about the same, a little denser than what we had, but similar kind of behavior that explains this concave upward shape of our curves. So I'm plotting here the bending moment in the pile before liquefaction at that same load level. I'm plotting bending moment after liquefaction. You can see that we've basically doubled the bending moment demand for the structure because the soil has such low resistance that it allows greater deflections. So we'd certainly need to account for that. We did a back analysis to generate PY curves that would be representative of liquefied soil. And you can see also, like we'd expect from a triaxial shear test, that they have a concave upward shape. These are tests at near the ground surface, 2 meters down, and all these tests have an excess pore pressure ratio of about 95% or more. And as you go deeper in the ground, the PY curves get a little stiffer due to the greater confining pressure. This shows curves for 100% essentially liquefied soil, and as the pore pressure decreases, the PY curves get stiffer. Okay. So having that information, then we can develop plots using L-pile. We can put those PY curves into the model and calculate the bending moment versus depth in red. And you can see we're getting a good agreement with the measured strain that's on the pile. Should be the case that we've back calculated it to be that way. And this is the deflection at the top of the pile head in comparison with the computed deflection. Okay. Now, other approaches that people sometimes use is to consider the liquefied soil as an undrained, with an undrained strength approach. And they would say that undrained strength is equal to the residual strength of the liquefied soil, and use the soft clay curve shape. All right. So you could come to a curve like this or others similar to this and get the residual undrained shear strength as a function of the equivalent sand SPT blow count. So this could be like an average of the information that's available. This dark green curve would be at the lower bound value for undrained shear strength. Another approach is to take a P multiplier and reduce the soil resistance from the non-liquefied state to what it would be in the liquefied state. And this P multiplier, people have suggested values between 0.1 and 0.3. So you can see there will be a substantial decrease in the lateral resistance. So here's some curves that were proposed by Brandenburg in 2005. And this shows the range of values you could select for different blow counts that you might have in the sand. So something like 0.1 to 0.3, depending on your blow count. So this plot shows the measured pile load with the markers and the calculated pile load versus deflection for our test site at Treasure Island. And then you can see it has this concave up shape that's typical of dilating sands. What do we get if we would use the undrained strength of the clay? Well, we get a lower bound value here and an upper bound value here. And you can see we're significantly overestimating the lateral resistance on the pile at small deflections. Out here at larger deflections, we might get about the right value, and that's because these residual strength curves were developed for large displacements. What about if we use the P multiplier? Where in our case, if we would use those P multipliers, once again, we'd predict higher resistance on the pile in comparison to what we actually measured. But you can see here, as I plot the curve for no soil resistance that we compute with L-pile, initially, that's the case. We don't have very much resistance to begin with, but beyond that, maybe a couple inches, the measured resistance is much higher than the case if we just assume no soil resistance. So this would be an extremely conservative approach. These plots show a comparison between the bending moment in the pile versus depth and various assumptions. The blue curve is with no soil resistance, and here we're predicting moments that are much higher than what we measure. The green curves are for the undrained strength approach. We're underestimating the bending moment here at 15 kilonewton load, getting closer at 30, And at 60, we're not too far off. You know, that looks pretty good. But for that model to fit all the load increments is expecting a little too much from it. This is the P multiplier approach. And once again, we can't find a value that gives us the right bending moment versus depth for all the load levels that we're developing on the pile. In contrast, the concave up shape that we've developed for the P multiplier for the PY curves is doing a good job of matching the measured bending moments. So we think it's important to use a concave up shape to define the PY curves rather than the conventional curve that you might use for soft clay or non-liquefied sand scaled by a P multiplier. So we developed this equation that give you the P value as a function of Y for a relative density of 50%, which is what our tests were involving in a 12-inch pile. And if you follow those, you get the PY curves that matched our programs. Now, this has been incorporated into more recent versions of L-pile and group programs, so that can easily be used. So conclusions from the single pile test is that controlled blasting is providing a new method for evaluating liquefaction behavior in situ, which is pretty exciting. The lateral resistance that we're seeing develops due to negative pore pressure at large deflections. And our PY curve shape has a concave up shape, and there's a significant amount of movement, maybe 2 to 3 inches, to develop any significant P values. The PY curve shape stiffens with depth, and as the water pressure decreases, it stiffens it even more. So these equations are producing a good agreement with what we got for these 12-inch piles and a 50% relative density sand. Now, what about other diameters? How are they affected by this? Well, we had a good opportunity to see this because we had a 4-pile group here loading with this frame, so that they were loading the same displacement, and we're loading against a 2-foot shaft here. This is a video of the blast going off and the liquefaction taking place around the 2-foot shaft.
Whoa, what we've seen before.
Yeah,
What's up?
As we loaded the shaft
look at that.
laterally, this gap formed, and the water built up by liquefaction now comes to the surface, carrying sand particles with it.
Holy mackerel! Hold back the floodgates! Woohoo!
These tests were actually really pretty fun to
Right there, what do you
perform.
think? I think it did.
So look at the volume of water that's flowing out of that gap there, and out of holes in the surrounding soil. This is the 9-pile group here in a 3x3 arrangement, loading against a 3-foot shaft. And in addition to that, we had the opportunity to work on the Cooper River Bridge in Charleston, South Carolina, to replace these older structures that were not seismically safe and didn't handle the traffic either. The soil profile in Charleston consisted primarily of looser sands and silty sands. These soils were susceptible to liquefaction down to about 40 feet below the ground surface. Then we hit into a Cooper marl, a CH material with liquid limit between 50 and 150, was non-liquefiable. But you'll notice that there's a sandy clay in this zone from maybe 1 to 3 meters below the ground surface that we'll have to take into account as well. So here's the soil profile with the relative density interpreted from cone penetration tests and the friction angle. And for a relative density, we're seeing values between 50, 40, 50% in that range, okay, in this loose sand. This is a photo of Charleston off in the distance in Mount Pleasant. This bridge, cable stayed bridge, supports the structure over the Cooper River. And our test site was right down here. So we first did tests with the hydraulic jacks that were supplied by UC San Diego. This is our shaft. It's 8.5 feet in diameter. The red dots are the pore pressure transducers to monitor the water pressure that develops. And we set off first a set of explosives around this inner ring. And then for another test, we set off another ring of explosives. In this case, there were 4 levels of explosives. This is the 8.5 foot diameter test shaft. Here's the hydraulic actuators that could give us 1,000 kips of force. There's the reaction frame. And this is a reference beam to give us the deflections. So looking at that, in a large portion of the profile, we are seeing excess pore pressures, maybe between 90 and 100%. Some of these up here are lower, and you'll remember that that's the area where we had the CH material, so we couldn't liquefy them. Here's the lateral load deflection curve before blasting, and here's the lateral load deflection curves for the first blast. We put cycles out to about 10 centimeters, so what, 5 inches? And now it's taking maybe about 5 times more displacement to get the same deflection, or 5 times more deflection to get the same load as we had in the non-liquefied case. This is a lower deflection that we had for the piles at Treasure Island, the 12-inch piles, because we're not decreasing the resistance of the drilled shaft. It still keeps its same flexural resistance, but and so the overall resistance due to liquefaction is not as dramatic here. Okay. Nevertheless, as you compare the bending moment pre-blast, non-liquefied soil with the bending moment after, this is the depth of the liquefied sand here. You can see once again, we're doubling the bending moment demand the pile has to supply. And I'm going to, these are at basically about the same loads in each case, but the bending moment is higher after liquefaction. So let's take a look at those different cases. This is our equation for piles in the 12-inch piles, and we're going to use a P multiplier to account for the diameter effects. So this is this P sub D. It's an adjustment factor, a P multiplier, if you will, based on the diameter of the pile. So these are curves that were developed independently. This was a curve developed by UC San Diego, Scott Ashford and Thomas Weaver in red. And these are the black curves are for the 12-inch diameter pile with a P multiplier, constant P multiplier of 5.5, say. And the agreement between those curves developed completely independently is, to me, very remarkable and suggests that these PY curve shapes are the appropriate. But we need to account for that diameter effect. And so for the 9 pile group, we have a P multiplier of 5.56. For this pile group, the shafts at Charleston, South Carolina, we needed a P multiplier of 9 for these 8.5 foot diameter shafts. So this is a comparison of PY curves computed and measured. There's no good comparison there. That's in the clay materials. But we get beyond that, we start to see that this agreement with that P multiplier is really pretty good. So what we've suggested is using this P multiplier. This is based on the 3 tests at 3 different diameters at Treasure Island, and the test at Charleston, 8.5 foot diameter pile. And so this shows the curve shape to account for diameter effects. If you use those equations to give you your P multipliers, this is the agreement between L pile computed moments and moments from the curvature measured, and the deflection versus depth measured. This is at a higher load, still good agreement, and this is at a higher load still. So we're tracking along quite well with this PY curve shape multiplied by a constant P multiplier. Okay, so to account for diameter effects, the resistance is increasing. It's non-linearly with pile diameter. There's a simple P multiplier that can reasonably account for these diameter effects. Now, what about soil density effects? Well, we haven't done tests on, you can see ours are mostly at 50%, but we have colleagues at UC Davis, Wilson et al. Showed reports of tests in a centrifuge, and they did tests with a relative density of 55%, and you can clearly see these are cyclically loaded. You can clearly see that there's this dilation and a concave up shape at different depths below the ground surface. But if you have a looser sand with a relative density around 30 to 40%, those PY curves are almost flat. Likewise, if we take test results from Suzuki and Tokimatsu at a large shaking table in Japan, where they can almost do full-scale things, as they shake this at 30% relative density, the load deflection curve, or the PY curves here, are almost flat. As you go to 50%, you start seeing this concave up shape. And in the 65% density, they're even stiffer. Okay. So what we proposed in 2013 was to use a hybrid, like a composite PY curve shape. So we'd use the tilt treasure item liquefaction test curve combined with the residual strength curve, so that we don't just go off into never never land with arbitrarily high values. So what we do in our current model that's in L pile is we follow this treasure island curve and then break off so that we can use the residual strength value at higher displacements. Okay. So we're basically using the lower of the two models. If we had a sand with a residual strength of 6, we'd have a much lower residual strength here, and we'd track along the treasure island model until we reach that residual strength value, and we wouldn't go any higher than that. Okay, so we're trying to take advantage of everything we know from case histories and behavior of lateral spreads. We suggest in doing this that you use the residual undrained strength that's shown here as a function of blow count in the hybrid model. It's kind of on the lower end, not the very bottom, not the middle, but maybe about a third up. So how does this compare with tests, centrifuge tests and other shaking tests? Well, it actually does quite well. These are computed curves using this hybrid model for two different tests, two different piles. Here's the load versus deflection and the computed load deflection. And we're doing really quite well, within about 20%. So we've calibrated this now with centrifuge tests, large-scale shaking tests, blast liquefaction tests. And the typical error is plus or minus 25% on moment and displacement. Now, if 25% error makes you nervous, maybe you're in the wrong profession. I don't know, but an error of plus or minus 25% in geotechnical engineering, I think, is really pretty good. And the approach accounts for sand density and pile diameter effects as well. Lastly, we wanted to see if we could do some tests with dynamic loading. And so we're going to use the statnamic test. We did these tests at Charleston and Cooper River. And the idea here is we have this big sled. We can apply, we can combust fuel pellets in this combustion chamber. That will produce gases that will drive the sled off to the right. And as it launches off of the test pile, it will produce a horizontal pressure on the horizontal force on the foundation, which will cause it to deflect to the left. Okay, so here's my animation for what it's worth. So it's sliding off, and this is loading and deflecting to the left. Right. So we would, here's the combustion chamber. This is strapped on to the test pile. So this is a 100-ton statnamic rocket sled. It's brought snug up onto the combustion chamber. See, this is tied onto the shaft. There's the 8.5 shaft, 8.5 foot diameter shaft, 150 feet deep. So a full scale test, and this is going to launch off in that direction. And here's the results of the end of the test. It slid clear down to here. So let's see if this video will also work. So 4 decks of explosive going off to liquefy down to 40 feet. And that was done. We let the gases dissipate. We fired off the rocket. So I think that's something like 1,000 kips, about 2/10 of a second. The excess pour pressure that we generated found an escape route. So this was flowing out of one of the measurement pipes and did so for about 15 minutes as that 40-foot layer of sand dissipated. Then we reloaded the pile, set off the charges again, and it came even further away, even a bigger load. Right, so here's what the load versus deflection curves look like now. This is for the first load, so about 1,000 kips. This is 1,200 and maybe 1,500 kips maximum load. Have a kind of a peculiar shape here because we're recording the resistance due to static spring stiffness of the soil, the damping resistance, and the inertia force altogether. So what we have to do is we have accelerometers at different locations along the length of the pile. And so we know the mass associated with each accelerometer. We know the statnamic force. We can determine the velocity at each one of these locations. And by a trial and error, get a damping coefficient. And then we can take all these measured values and our estimated damping coefficient and compute the static resistance. Okay. That's quite an effort, but it's all doable. And here I'm showing you the static resistance from these 2 sets of load deflection curves for the 2 static load tests, cyclic load tests, I guess, from the hydraulic actuators. And then the blue curve is the equivalent static load deflection curve with eliminating the damping and the inertia forces. So if you squint a little bit there, I think you'll see that has basically the shape and the hysteretic behavior that you're seeing for the static resistance. And what did it take to do that? Well, it took a damping ratio of about 30 to 35% along the length of the pile. And when we use that approach, the equivalent static resistance is pretty consistent with the measured resistance that we had from hydraulic actuators. So we're seeing that liquefied soil does produce additional resistance due to damping in this case. Well, that's, I think I'm right on time. Yeah, about 50 minutes in, and that's what they asked me to do. I've put references here that will give you some information, background information on the various tests that I've described here. And you can look those up. I understand this is going to be posted, so you'll be able to access any of these references. And then I've also included references on passive force, because the passive force deflection relationship is also really critical in deciding how a structure would perform if lateral spreading develops along the side of the structure. All right. We'll see if there are any questions.
For any of the attendees, if you have a question for Dr. Rollins, please just type it into the Q&A chat box and we'll see it. Okay, we do have one question for you. For laterally spreading soil with a non-liquefiable cap, do you find that the pressure acting on the pile within the non-liquefied zone is equivalent to the passive resistance in the soil?
That's a good question. We've had some experiences where we've loaded with a weaker layer underneath the zone that's against the pile cap. And in cases like that, we've had a greater amount of deflection required to get the full passive force. And I know there have been some tests at UC Davis that show that you might have more lateral displacement required to get the full passive resistance. So there could be a case like that if your resistance, or if your liquefied zone is immediately below the pile cap that's producing the passive force on it. But we have simulated these from our field tests, and with the liquefied soil, it seems like it works reasonably well. There are certainly going to be differences between what we measure for our passive force versus deflection curves from our static resistance and from our dynamic behavior in the field. And that's going to lead to likely larger dynamic forces, but the lateral spreading is likely to occur after the shaking is stopped in a lot of cases. So I think this is a good first approximation of what's going on.
All right, Dr. Rollins, we have another question come in. I've read a few articles, kind of state of art and practice in relatively level ground. Lateral spread could also occur. What's your opinion on this?
Yeah, lateral spreading can develop with very small slopes, even almost like 1 to 4% slopes. So, but it usually needs to have a free face somewhere to where the soil can slide to. So if you've got a large river adjacent to the structure you're concerned about. We saw some in Croatia, earthquake there in 2019, where the slope was essentially flat, but they had a very deeply incised riverbank, and that led to some lateral spreading taking place. So yes, it doesn't, even if it looks like it might be flat, you can still have lateral spreads if there is a big offset in the vertical dimension. A free face.
Okay, thank you. I hope that answers the questions. Are there any others? Follow up to that, how far would the free face be to cause that? Or could it be?
What I'd recommend is you use the multilinear regression curves equations that were developed by Youde et al. And Steve Bartlett and others, and that will let you predict the lateral displacements that would occur at different distances back from the free face. So it's going to decrease with distance from the free face. The lateral displacement will decrease with distance from the free face. Right close to the free face, you may also have features that are associated with slope failure or slumping, and those displacements might be much higher than even that are predicted by the Youde et al. Lateral spread displacement equations. But if you're back a ways from the edge of the river, one height usually of the offset, then you can use those equations.
Okay, we have another question. With the action of lateral spreading and the bridge abutment going towards the free face, how does passive resistance develop behind the abutment?
It happens, it looks like that you might be tempted to say, oh, that's an active earth pressure case, right? Because the wall is moving towards the river, but the soil is moving more than the bridge abutment is moving. And so as it's putting the soil in compression rather than extension, so that creates a passive force condition, even though it might look to you to initially to be an active condition. We've seen cases when I was in Chile, we've seen cases where the bridge, the pressure on the back of the wing walls just wraps the ring wall or shears it off of the abutment wall. Okay, that pressure is causing a compressive force, and that happens because the structural resistance of the foundation is enough to have it move less laterally than the soil behind it is moving in the lateral spread. Okay. So that creates the passive force.
Very good, thank you. Any other questions for Dr. Rollins? No, looks like that might wrap it up.
Okay.
So with that, I would like to, on behalf of DFI and everyone attending, again, thank you, Dr. Rollins, for a very interesting and informative presentation. As you can see, PDH certificates will be available for paid registrants after you complete the webinar evaluation through the event module, which you will get instructions via email. You can register for other webinars at www.dfi.org. The next What's Shaking webinar will be in early December, tentatively scheduled with Dr. Armin Studline. With that, just my concluding remark is some people get to have all the fun. Um, setting off explosions for science and research. So thank you again to everybody attending. Thank you, Dr. Rollins. Thank you, DFI, for organizing this webinar. We'll see you next time.